Hello, I'm Andra Petrovai, and I'm excited to present our work on a self-supervised monocular depth estimation approach to depth-aware video panoptic segmentation. To obtain a holistic 4D representation of the environment across space and time, depth-aware video panoptic segmentation is introduced as the combination of monocular depth estimation and video panoptic segmentation, where we have temporally consistent instance identifiers. Compared to the straightforward approach to use separate networks for each subtask, which incurs high computational costs, multitask learning is more attractive because it reduces the latency by unifying all the tasks under a single architecture. However, multitask training is challenging and performance degradation for one task can be observed. Previous works use fully supervised learning, but large-scale acquisition of depth ground truth and panoptic labels is difficult and expensive. In this work, we aim to reduce the ground truth dependency and introduce MonoDVPS, a multitask network with mixed training regimes. Depth estimation is trained in a self-supervised manner without labels, while video panoptic segmentation is trained semi-supervised on panoptic labels and pseudo-labels. In the complex multitask training setting, we aim to improve the performance of all subtasks and use large amounts of unlabeled data and introduce panoptic guidance for improved depth performance. Our network architecture is based on the image panoptic segmentation network panoptic deep lab with several changes. We also introduce a depth head and multi-scale depth predictions on top of the semantic decoder, and finally we extend the backbone in an optical flow decoder and head. We employ self-supervised monocular depth estimation, which uses no ground truth. During training, sequential triplets of frames are required, and the ego motion estimation network is jointly trained. The mechanism is based on geometric projection and is formulated as the minimization of photometric errors between synthesized adjacent frames and the current frame. We generate pseudo-labels for the unlabeled data on the Cityscapes-DVPS train set with a panoptic segmentation network and extend the dataset almost 6 times. For improved panoptic pseudo-labels, we apply test time augmentations. In self-supervised depth estimation, the scene is assumed to be static, and moving objects corrupt the training signal. We propose a method to detect moving objects based on the panoptic segmentation and remove those locations from the photometric loss computation. The idea behind this algorithm is to measure the overlap between the instance mass of the target and the synthesized image, obtained using adjacent frames, and the predicted depth. Static objects in the scene should have large overlaps since the 3D projection models use only the ego motion, while moving objects should have a small overlap. We also introduce 3 panoptic-guided depth losses to improve depth training. The idea behind these losses is that there should be a small depth difference of adjacent positions inside the panoptic segment and large depth differences across the panoptic edge. We perform extensive experiments on the Cityscapes-DVPS and SemKITTI-DVPS datasets. We present here our ablation experiments, which demonstrate that panoptic-guided depth mechanisms are effective. Also, training the network with large amounts of unlabeled images brings the most benefit. We evaluate our network for the depth-aware video panoptic segmentation task. When using the same backbone, ResNet50, we surpass the state-of-the-art VIP Deep Lab network and obtain a faster inference time. We present qualitative results. On the left, we have the image, while on the right, the video panoptic segmentation and depth prediction. Thank you for your attention, and feel free to reach out for any questions.